It's, I guess, just to give you perspective. So I live up in the Yukon. I've been keeping bees for almost 10 years, a bit more than 10 years in a couple of locations. Uh, I do have an engineering background, so you'll see that there are lots of charts, but in my final version of this presentation, there'll be fewer. As you know, the whole insulating thing is a hot topic, and tons of people have different opinions, or there's a lot of anecdotal evidence or experiences. So I want to live in facts. Hence the reason I've been monitoring and observing my bees now for at least 5 years, 6 years. I've been collecting my own data. So for example, a double had about 25 sensors, and a single, usually when I do monitoring on them, there's about 13 to 14 sensors in it. I do have weight scales in the summer, and I do IR thermography to have a look at the cluster. So I stick my camera through the entrance and look upwards into the cluster. I have a microscope, so I've been tracking disease, nosema, and now something called amoeba disease or amoeba cysts. I'll talk a bit about that. I also do pollen analysis now and honey analysis. And yeah, so you'll see that I'm a very data-driven beekeeper. It's just because I want the facts and I don't want too many assumptions. But yeah, so like I said, we'll go. It's probably an hour, at least an hour and a half. The target audience is actually, it's probably intermediate level. Beginners, the challenge with beginners is I was a beginner at one point. It's called the Dunning-Kruger effect. You think after 1 or 2 years, you know everything there is to be known about bees, and then you get an awakening. So despite me doing it 10 years and doing all these studies, I realized that I still know nothing. I know a lot, but there's still tons to learn, and it's a never-ending process of learning new things. So my goal is to basically show you what you may not know, so that you can grow and learn. And Bernie, I'll mute you. So yeah, so we'll get going. So this front chart here, I put this together maybe 3 years ago, and it was from the papers I've been studying, from all the, I guess, my early observing the issues I was having with nosema and different things. And I started identifying 3 streams of things that I needed to understand to become a better beekeeper and actually improve my wintering. So if you know, I don't lose many bees in the winter. When I first started, my clusters were fairly small coming out of winter. And now my clusters in a single, there might be 6 to 8, 9 frames of bees coming out of winter on my singles. And a doubles, they're in the 12 to 16 frames of bees. So they're nice big clusters. My winter here goes from probably October to mid-April, sometimes early May. Last year it was early May before the snow was gone, or mid-May. So just to give you perspective. But bees are special. They're adaptable. They're wonderful insects, social insects, but they cannot defy the laws of physics. So what I'm going to try to do is I'm looking for the why of a few different things. Okay, so the how and the what really depends on where you're from and what your conditions are. But if you understand why you need to do something or what may happen, then it helps you make better decisions. So from a health perspective, we all know our bees need to be healthy, so you need to manage your mites. So these blue boxes up here, these are things, every time you see a little beekeeper here, it's things a beekeeper has control over. Okay, so manage mites, We do have control around winter bees and making sure that our colonies are, if you need to feed pollen, to keep the queen laying later in the season because there was a pollen dearth. Those are things we can control to make sure that we have a nice healthy population of winter bees. Again, numerous bees, young queen. So those go hand in hand. So typically 2 years is the max that I'll, for queen age, that I'll have in a production colony. I may demote her and put her in a nuke box and overwinter her as a spare queen, and then to help build resources. But in my main colonies, I try to keep my queens basically the third winter is in a nuke box. But I get them to overwinter at least 2 winters. And then after that, if they've been successful, I'll keep them as long as they live, but in a different format. From a disease perspective, there's nosema, mites, and this is not a disease, but small clusters. So in the Yukon, our summers are fairly short. So we tend to do our splits and raise queens late June, July. So sometimes our colonies don't have much time to grow into big doubles. So we have to make decisions on housing our bees in a smaller volume. Okay, so I've successfully overwintered 5-frame nooks up here, singles and doubles. My favorite volume is actually singles. And I have basically I'm 100%, so I have 15 successful overwinters in my singles, and I've got my doubles, I think I'm around 80% success, and my nooks, I've done it 3 times now, and I'm at 60-some percent. They tend to make it, depending on the cold in April, depends. That's the main contributor. This middle one, the food, there's a lot of information. I could talk about an hour on this slide, but just to show you, most literature, they always give you a minimum amount of honey you need in your boxes to successfully overwinter. So the key is make sure you have more than what they recommend. Okay, so up here, for example, my doubles, they could make the winter with 50 pounds of honey. But I make sure that a double has 100 pounds. Okay, they'll only consume about half of that. So, and that's my goal. And for my singles, they consume about 30 pounds from October to May. And I usually make sure that that box is around 60 pounds going into winter. The critical food is important, but this thermal mass, having honey in your boxes, especially on those outer frames, is critical for you to have a successful overwinter, because it's a thermal lag, a thermal mass, so it helps reduce the impact of those temperature changes. So in my presentation, I'll cover that because it's kind of critical. Let's see, because if you don't have enough food, then you'll get really crazy temperature swings, especially if you're not insulating. Okay, and again, depending where you are, you may not need insulation, but there are benefits to insulation. And then the last one here is where I'll spend most of my time. It's the enclosure, because you can balance insulation. You can have for me, when I overwinter, this hive volume to the number of bees is my critical ratio. And that's how I decide what volume to overwinter my colonies. And then the last one here is the amount of ventilation you want in your box. So I'm 100% passive. I don't use any top entrances at all. So passive means it's all natural currents, natural convection, and it's based on temperature differences, and I'll cover what that is. And active is Vivaldi boards, quilt boards with all holes, top entrances. That's what active is. Again, I'll show you that if you go with the top entrance, and especially if you're insulated, you need to be careful. There's some things you need to watch out for. And then there's different types of honeys in your colony. And just so you know, a typical cluster releases about 5 to 20 watts of energy. And that basically in an insulated colony, I'll show you how it actually maintains a temperature, a decent temperature in the colony or in the box. And if you've got a top entrance, you lose some of that heat. If you've got no insulation on top, you're going to lose some more. So there's a lot of different criteria. Oops. Okay, so again, my goal is not to convince you to do something. It's to help me and you and us understand why and how things happen in our boxes. And again, if you've got a theory question, I can do my best to answer it. And that's what I'm trying to figure out. Because there's some studies out there, but many of the studies are black box studies where they're just measuring survival rates. They had 100 colonies set up one way, another 100 colonies set up a different way, and then they just measure success rates at the end of the season, and that's the I guess that's the outcome of the experiment. And there's not enough, I guess, being an engineer, I want some proofs around why it worked and why it didn't work, and that's what I'm trying to figure out. These are the inside edge of the coast mountains. So about 100 kilometers over these mountains is Skagway, Alaska. And we're on the cold side, they're on the warm side. Okay, so my house, we've got gardens, chickens, but it's a mix spruce and lodgepole pine forest with some spruce, not some spruce, some poplar, aspen, and willow. And in my area, there's not much for non-native flowers. So there's a bit of sweet clover that I planted over here, and that's about it. And then our garden over here. So yeah. So, but just so you know, even in our short growing season, we can grow cabbages and napas and potatoes, carrots, and all that type of stuff. So our cellar gets filled with veggies. So my bees, the thing about the Yukon and a lot of boreal forest settings is we're forage limited because there's not many non-invasives or non-natives, I should say. So we can't have, if there hasn't been a forest fire in the area, we can't have more than say 2 to 4 colonies per location. If they're closer to town, there's more gardens and more clovers and stuff, so they can have a few more. But where I'm at, I have to minimize. So my goal is, 2 to 4 is max, or else I won't get any honey because it gets divided up. So most of my yards can produce about 200 pounds of honey per yard. So if I've got too many colonies, it just means that surplus gets divided up by those number of colonies. So my goal is to have 2 production colonies per yard, and then that way I can get my 50 pounds of really beautiful Yukon honey per yard. So I use all polystyrene hives, and you'll understand why I do it, because our evenings are like some people's winters in the summer. So I'll be using mostly Celsius, because that's temperatures I know, but I'll be using pounds and inches. But let's see. So our evenings in my location, we get maybe frosts pretty much any time of the year. But our typical summer evening or morning temperature is around 5 to 10 degrees Celsius, and our day high is about 20 to 25 if we're lucky. Mostly Carniolan queens. I used to get my Nooks from BC. I still get some queens from there, and I bring some Saskatchewans. So I haven't bought bees in about 4 years now, and my goal is to be sustainable. I will bring queens in for genetics, but I do my splits. I always keep 2 super duper colonies that I split and create Nooks with, and resource colonies, just to make sure that I never have to buy bees again. And because I only lose maybe one colony in late spring, uh, basically I'm able to grow my apiary every year if I wanted to, but I'm trying to maintain it to 10. Mites, I don't really have mite issues. I've experimented with mites, letting them get out of control. But this year, my goal is to completely get rid of them. So I'm gonna, because we're isolated, most of us, so there's no other beekeepers around. I don't bring bees in, so if I manage my mites properly. So I have one yard with close to 0 mites. And then the other yard has high mites, but I did a Formic Pro at the end of the season just to knock them down. One reason I like asking questions and solving problems. So the mindset I've been doing is you've got to be curious, especially for beginners, pretty much anybody. Be curious. Don't like, I'm stubborn, but it's important that you be curious and ask why questions. So ask open-ended questions, because if you're gonna ask, do I do this or do I do that? The answer will be yes or no, but you won't really understand why or how it should be done. You'll just understand the what. So it's critical that you ask the right questions. Be curious again, and look for different perspectives. And try to see the world around your colonies and your bee yards from the bee's perspective, okay? Don't look at it from a human perspective. So the more you learn about bee behavior and bee biology and the environment and the flowers and the forage and the pests and all that, the more you'll get enjoyment in this hobby, and the more you'll be able to understand why things happen. Key one is learn to experiment. So if you've got 4 colonies, try something new in one of them, okay? And not too much. You want to tweak little things here and there. One thing I've learned is people know more than me, okay? So if you approach a conversation with you knowing more, you've just shut yourself off. So it's important that you be humble and learn to listen to other people's opinions and then share with others. So teaching is a great way to learn. So again, be curious. I always have my phone. I walk a lot. I hike a lot. I'm the only beekeeper in my area, so if I see a bee on a spruce tree, I know it's my bee. Okay, so over here, this is like a swamp marsh marigold or marsh fleawort, I think it was. And there was some flooding around the lake here, about half a kilometer away, and it was just jam-packed with my bees. So I was like, a new nectar source. Over here, so this is a fireweed. Mid-August, it gets affected by frost because it's starting to die out. And then my bees were all over the dead patch of fireweed, and they had this orange pollen-looking thing. It's not pollen, it's actually rust spores, and they're collecting it off these leaves. Okay, so being observant is really critical. And this here, I think it was probably a hornet or some type of yellow jacket that the bees balled and cooked because they probably invaded the colony. Okay, so this is part of my understanding my pollens and the different things. So I collect a lot of flowers and I pull the pollens off of them to make my reference lines. So even despite me enjoying hive monitoring and having sensors and all that in my colonies, my best monitoring tool is still me. It's my senses. So I do have a gut sense over here. You start gaining that with experience, but taste. So I taste my honey, different taste of honey or different smells. Your colony has sounds. A nice, healthy, strong colony will have a certain sound. A pissed off colony or a queenless colony have a different sound. Touch, vision. So those are your best monitoring tools. And the more you educate yourself, again, around biology, behaviors, your environmental cues. So for example, here, I'd say maybe 2-3 weeks after the dandelion starts blooming, is when we need to be cognizant of swarming and then start watching for swarm signs. So typically 3 weeks is too late. So at probably a week to two after a dandelion start, I have to start watching out for swarms, or swarm signs, I should say. So I've done, because most of our advice up north, like Alaska and Yukon, we get from the south, we get from these areas here, so, or southern Canada. So it's important that we understand the differences. Okay, so I'm in zone 2. So in this dark blue area here. Okay, so I think coastal Alaska is over here, interior Alaska is like Dawson City. There's Yellowknife. So the importance of this chart here, it helps you understand how much heating and how much food your bees would need in a non-insulated colony. Okay, so I'll explain that in the next slide. Over here, these are just, it's called heating degree days. I just call them cluster degree days, but it's the same as heating degree days. They're just it's like growing degree days, but on the opposite side, from the cold side. And it's proportional to how much heating is required inside a colony or inside your house. Okay, so you can see I'm over here, Fairbanks is over here. I think I had Palmer numbers when I went down there a few years ago. I think they're close to Prince George. And Palmer, Wasilla is around here. Mike Palmer in Vermont is actually 48. What's his name? Ian Stepler is around Winnipeg. And you can see how there's different locations. Mike Bush is actually over in Nebraska. So there's a lot of different things. Okay, so it just gives you perspective about if you're down here. Importance is you need to have enough stores, and you'll notice, I'll explain why insulation or having follow boards, insulated follow boards, might help you with your springtime ramp up and eliminate some of the starvation risk. I'm not going to go too much time, but I'll just flip up one. So these lines here, this is the same value. So this red here, the area below the red here, the sum of all those is this bar here. Okay, so what I've done a bee year. I was doing a talk for a group in Wisconsin, and it was just to compare the winter. Okay, so again, the bigger the number or the lower the number, I think minus 45 here is a full day at minus 30 Celsius. And anything around minus 50, it's a minus 40 day during the night, and then minus 35 during the day. So it just gives you an order of magnitude of how cold it is. Say in Whitehorse, you can see a lot of the evenings are actually below 8 degrees, actually below 10 degrees Celsius. Okay, so these are degrees below that temperature threshold. In Wisconsin, you can see the nights are much warmer. Okay, but you can see that early spring, the evenings are quite cool. Okay, so the brood starts over here. It means at night, that colony, if it's not insulated, or if it's not set up properly or doesn't have enough food, it's still, this is why they starve in spring, is because there's a heating requirement and they need to stay warm. Because once brood rearing starts, they go from maintaining, say, 20 degrees Celsius, 18 degrees in the core of the cluster, and then they try to maintain a 35 degrees Celsius or 95 F across multiple frames, which is the stress point. So again, know your flowers, know when they're blooming. For example, in the Yukon, a lot of our honeys actually have willow. because we've got the early willows, which bloom late April, early May, but we've got some that are actually blooming and flowering into July. And the male catkins actually produce nectar and pollen. So they're actually a good nectar source. So you can see we do have sweet clover and stuff along the roadways, but those are some of our key nectar producing plants. Be curious again. So I bought this pollen collector from Amazon. I think it was 20 bucks. I ran it probably for 2-3 hours every 2 weeks. And then I collected baggies of pollen. So it gives me an idea of the different colors, so the variety, how much, okay, for different times of the year. And towards the end of pretty much July, early August, the volume of pollen here really drops. So now I actually feed pollen patties from end of July, just to make sure that the bees have enough to produce the winter bees, and also to mitigate that rust collection, because the bees start collecting rust spores, and I guess it's low nutrition and it's not really good for the bees. Okay, and actually these red dots here, those are rust spores from the rose family, the wild rose up here. So key to successful overwintering is simple, just healthy bees and reduce the stressors. And if you can, do things to improve your local environment. So if you remember that first picture I showed you, the drone shot of my property, the sweet clover. The reason I put sweet clover and sainfoin is to help with, because they're frost resistant, and they'll stay blooming until probably the first snow into September. So it gives the bees something to forage, or else they'll be foraging rust spores off trees or going for honeydew on the aphids at the end of the season. So bee stressors, let's see, bee stressors. Beekeepers. Beekeepers are a big, you going into the colony being worried that they don't have enough food. So that's a bee stressor. Okay, so I'll show you how I set up my colony so I can actually have a quick look, but without opening up the colony. And then if conditions are right and the bees have done their late winter cleanse, then I start adding my pollen patties without actually disturbing the colony. Okay, so lack of food, the quality of pollen. Basically, if it's warm and then you get a polar vortex in the late winter, early spring, the bees start brood rearing, and then the cold hits, it'll stress the bees out. If you've had a cold winter and then the bees have to generate a lot of energy to stay warm, then they'll age quicker. Okay, so cold stress is fluctuating temperatures. It's diurnal temperature. So in the morning, it's -30 Celsius, and then in the day, it goes up to like -5, which is a typical Yukon late winter, early spring type of weather. There's diseases, so nosema and stuff like that, and all the virus related things. So our goal is to eliminate as many of these as possible to make sure the bees can live as long as possible. So we've all lost colonies. If you haven't, one day you will. But when you do lose it, just know that most of the reasons why our colonies fail is us. If you say the weather, if you say starvation, if you say mites, it's actually beekeeper. It's something you did not do to help your bees out to reduce that stressor. So the root cause, the simple cause is actually those things, but the root cause is it might be a lack of knowledge, or you don't have a consistent approach yet, or you didn't make sure that you waited too long to feed them in the fall. You took too much honey out. you didn't manage the pests. Some of the diseases, they just happen out of the blue and they're hard to control. So like nosema, it's one of those diseases that you can treat for, but it probably won't make a difference. Poor hive setup, and then trying to overwinter a weak colony in a very large volume. And that's a typical beginner type mistake. And I'll show you some pictures of what I do to mitigate that. So if it's even smaller than a single, I've got some special boards that I use to reduce the volume. So currently, a lot of people blame mites for their failures, okay? Likely, very doubtful that mites is the only reason why that colony failed. We call it a Swiss cheese model. Failure model is there's multiple things that need to happen for that colony to fail. And there's likely other contributing factors, okay? So there's so many variables. And the more you learn about bees, the more you'll see that, wow, there is a lot of variables. So is the general health, the age of those winter bees. So for example, I've got 3-4 things killing my bees right now. Okay, so all 100% of my colonies are alive and well right now. One is struggling with nosema and this amoeba disease. But in the other ones, when I collect dead bees and I check their guts to see what's going on, a lot of them have rust spores in their guts. And they have a lot of funny things in their guts. So it's probably an indicator for me to look at nutrition next year and to make sure that I might have to feed pollen patties a bit longer or earlier than I did this year. Queen age. When I first started, I was trying to get 4 or 5 years out of my queens, and they die at 3.5, 4, and then I'd struggle to find replacement queens. Hence the reason now I replace them at 2.5 years. I retire them. If they're not really producing well, I'll pinch them. I don't like pinching queens, but I'll pinch them if I have to, and then I'll replace them. And if it's a good queen and she's 3 years old but still laying and still healthy, I'll have her in a nook, and then she becomes an emergency queen. If I need her because I've lost a queen or I've rolled a queen, then at least I've got a backup queen. We're going to talk a bit about the hive properties. So, but if you get hit with, say, it was 45, 50 Fahrenheit, 10 degrees Fahrenheit or Celsius or so, and then it drops to minus 20, 30 Celsius in the evening or in the morning, and your bees die, and those are the things you need to understand. If there's a risk, and for example, in the Yukon, it's about $375 for a nook. So I can't afford to be buying nooks every year because it's just not sustainable. So the quality of the food, water management. So because there's no cleanse here, so they cleanse probably in October. There've been some minor cleansing this week because it's a bit warmer than usual, but there hasn't been a major cleanse yet. So which impacts potential water, and it increases the risk of dysentery. Nosema by itself doesn't seem to be a problem, but nosema mixed in with other things seems to be a problem. And again, beekeepers tend to pop the lid on some colonies a lot and add some sugar and do all these candy board things. So it does cause the bees some stress. Okay, so this is my one setup. So this is actually the top of the colony, and I'll show you some colonies at the end of the slide, but I've got this contraption that I've built where there's an open slot in the middle and I can put fondant in there. So usually in the fall, I'll just put some hard sugar just to plug it off or some fondant. And then come spring, usually March 15th is my target. There's still tons of snow. This was actually April 26th, I think. last year, so there was tons of snow, no forage, no nothing. But the bees, I added pollen patties. This was a warm day, so the snow was just covered with bee poo. So I knew they had cleansed. Okay, so the instant I add a pollen patty on my colonies, let's say within 2 hours, that colony is bringing up the temperature to 35°C, and the queen is going to start laying. Okay, the reason I do that is 1 month to 3 weeks after I do that, I'm doing my first inspection. I want to see if my queen is healthy. And because our season's so short, I artificially feed probably 3 weeks to a month before the season really starts, so that the queen is either laying or not laying. If she's not laying, I know there's a problem. But if she's laying and there's a really nice brood pattern and mixed brood and emerging bees, then I'm happy. And chances are that queen's going to do well. In the next slide, I'll go through why I wouldn't do it, or how I decide when to start pollen patties in late winter. Okay, so again, this is an example of a March cluster, an April cluster, and they're big clusters. They're doing good. This is a 5-frame nook I overwintered. It became a really strong single by mid-May, June, early June, and it was ready to produce honey for the July flow. So the pollen patties in late winter, I won't put them on until there's a cleansing flight. Okay, because if I put pollen patties on too early without a cleansing flight, I risk dysentery, I risk bunging up the bees and having poo in the colony, and it's not worth it. So what I typically do is I wait for the first warm day. If it's warm outside, I'll put my bee suit on, I'll go out in the yard, if the bees are all cleansing outside, I'll put a pollen patty on, but I won't do it until the bees have actually cleansed first. Now that I have a set system, I've never had a colony starve, and I know how much honey is in all my colonies, so I don't need to worry about starvation. But if you're worried about starvation, then by putting a pollen patty on, you run a risk of starvation. The other caveat here is my colonies are well insulated. And just to put things in perspective, my single, or my double here, consumes about 50 pounds of honey from October to May. Okay, so I think it was in Maryland, because I collected some data there. Their colonies consume 50 pounds from, I think it was late November to March. Okay, in less than half the winter, they consumed as much honey as I do here. So the risk here is, what's the risk of a cold snap? And some people take off their wrappings too early. Okay, so it's important that you leave your wrapping on for at least the first brood cycle to second brood cycle, so that they have plenty of fresh new bees to keep that nest warm. Because if you take the wrapping off too early, you're going to stress those bees out, you're going to increase mortality, and chances are you're going to stunt their growth, because then they won't be able to keep the nest warm. So if you're going to wrap, leave it on for at least 2 brood cycles in the late winter, early spring, and that way you're guaranteed that a cold snap won't hurt them, and you'll get a couple of rounds of really healthy spring bees. And the other one is, I'll get to you in a minute, Angela. So can you feed your colonies without major disturbances? So some people have to pop lids, pop boxes off, and all these things. So it does cause distress. So the earlier in the winter or late winter that you do it, early spring, the more disturbance you might cause that colony, and the more you might hinder it. Angela?
Hi, can you go into greater detail about what conditions you're going to reduce the volume, whether it's a single or a double? What's the temperature outside when you do it? How invasive of a process is it? for those of us that are still having some pretty chilly days in the spring.
Yeah, sounds good. So I'll cover it a bit more later, but just to talk about it briefly here is I will do it in my cutoff is usually mid-August. Okay, so for determining what size it'll overwinter, it'll be, I'll have a look at the cluster size, and then I'll make a call. Do I do a double, single, or 5-frame nook? And that's my mid-August decision. And then usually late April is my first inspection. And then if they're cleansing, I'll do a quick one. So typically, let's see, do I have it? I'll just go back to the dead out. There we go. This one here. So for example, this double here, so this was the cluster in the top box. The bottom box was empty. It was actually frozen in. So the bees were top box bound, because that's a challenge with polystyrene. If there's not enough bees, is they can't generate enough heat to thaw some of the space sometimes. So if I left them like that, they're going to die. It did have nosema, and it probably had that amoeba disease too, so it eventually died in late May. But I have no choice. So if I leave it that way, it's going to die. So what I'll do is I try to keep the box that has the most bees. I just pull this box out, and luckily there was no bees in there, because there was no bees coming out, because they were frozen in the top box. So I just pulled it out. So I think it was first inspection, so it was probably 10 Celsius, 10, 15 Celsius. So it was plenty warm to do a quick pop out. So before I pull frames, it'll be a bit warmer than that. It's usually 15 degrees Celsius before I start popping frames. But that's just an example of what I do, is I just pull this box out, drop that on the bottom board, and it was good. And you can see how there was ice buildup around it too. And this dysentery nosema was actually from 2017, when I had honeydew for the first time. Okay. So again, this is just connecting the dots. So some of us have microscopes or access to a microscope. And I was going to say, some of these are really good high school student projects, because sometimes biology teachers are looking for projects for the kids, and you can provide them with pollens, you can provide them with bees, and then they can actually learn about bee biology and different things. So this, for example, it was full of these orangey red dots, and I was just, the green stuff here, the dark stuff, that's fireweed. The yellow was some brassicas, and then the sort of orange I was curious with, and it was actually the rust that grows on the wild roses. And then you can see in my bee guts these same spores, or the fungal spores, and then in the honeydew honey you can actually see these fungal spores and fireweed. So there's a lot of things you can look at to try to connect the dots. Just because I see it there does not mean it's a cause. Correlation or seeing it doesn't mean that it is that, but it shows a connection. And these little things in the background here, these are all nosema spores. Okay, so, and be observant. So 2018, 17, every time it dropped to minus 35, 40, there'd be thousands of dead bees in front of my colony. And I was like, that's not normal. And people are saying, oh yeah, it's normal to have dead bees. But then I said, a few hundred, 50 to 100, yes, but not to the level I was getting here. So this is where I made the decision to buy a microscope, and I collected some of the dead bees, and this is where I started seeing that all these dead bees had nosema. And then the following year is when I started noticing these cysts, these little globes. Again, you can see that there was a healthy hive here. It went through winter wonderfully. but there was no dead bees. And then the one right next to it had a bunch of dead bees. I collect these dead bees, a few dead bees here, and nosema, no nosema. But now I'm noticing something else. I'm noticing these globes. So here are my wintering successes. You can see 2018, I had 3 colonies, they all died. My honeydew honey was actually really low sugar content. Okay, so glucose, fructose was around 50 grams per 100 gram versus a typical 65 to 73 grams per 100 gram of what a typical honey is. So this is fuel, this is winter fuel. So it means they needed 25% more honey to produce the same amount of energy to stay warm. It's honeydew honey, so it has all this stuff in it they can digest. And you can see how this dysentery and these dead bees, there was a link there. Okay, so this is this year. So this was a couple weeks ago. So I have 1 colony that's spitting out dead bees. So the fun thing with having a microscope and some practice now is I pull some bees out. I do some gut tests. So I just squish the guts out onto a slide. I put a slip on it, have a look. And then I was seeing these globes. And then from the literature, I was like, pretty sure these are amoeba disease. There's not much for reference pictures. So then I taught myself how to dissect the bees and pull out the digestive tract so I can have a look at it. And then this is a picture of what I'm guessing it's Malpighian tubules. And you can see it's got all these cysts in here. And this is consistent with what the references online look like. And so I've sent a lab now, 2 vials full of bees to the lab in Florida for them to analyze, because there's a pathologist there that's really interested in this. So she hopefully will be able to help me. How are we doing? Any questions before we jump into engineering physics? Good? Okay, sounds good. So this here, the next few slides will be more, I guess they are more complicated, but I'm going to show you some relationships. So these lines here are drawn from, just to give you an example, when I monitored last year, I collected over, it was close to 1 million data points. Okay, so it's like 33 sensors times 4,000 each. Plus a bunch of calculated values, plus 5-minute weather data. So it's all this data that I've been collecting, and data is only good if you do something with it. And there's a challenge is I've got so much data now that I have to be careful, because too much data is actually not good. So there's a right balance. So the gray, the orange, and blue lines, these are insulated colonies. Okay, these are my colonies. The yellow line is a colony in Virginia, and it's actually from the fellow from Broodminder, so Tio, and he's the one who gave me the idea of putting 9 sensors on top of the box, and then he gave me an idea of how to model the temperature distribution. Okay, so this is his data. And what we study when you read books and stuff, they always say that in winter, the temperature outside, so that's the x-axis here, is very close to the temperature outside the cluster. Okay, so in the yellow colony here, so the wooden colony, it's true. So the correlation, the R2 is more than 9 or 0.9. So it says that it's very correlated, and there's a strong relationship between the inside and outside temperature. In insulated colonies, it's around 0.5, so it doesn't agree. So there is a difference. So the difference here is that insulation factor. Okay, so you can see that at -40 outside, the measured temperature inside was anywhere from -5 to about 5 or 6 degrees, depending on the size. So the gray line is a single, and the orange and blue is The blue is the bottom box of a double, and the orange is the top box of the double. So now if I move over here, so being an engineer, calculating heat losses for a box is actually fairly easy. So it's just the surface area in metric, it's easier to use metric. So it's like the R value, but in metric. And then the temperature difference gives you a pretty good estimate of the heat loss. So in the insulated colonies, when I took all this data and I calculated the heat loss, the relationship between the outside temperature and the heat loss is again 0.9. So it's more than 0.9. So it says there's a very strong relationship there. In the wooden colony, okay, so over here I've got heat loss versus outside temperature. In the wooden colony, when there's no brood, so this is the key one, when there's no brood in that colony, there's no correlation between heat loss and outside temperature. There's very little relationship. Okay, so hence the reason why, because the driving mechanism of that cluster is actually the cluster itself, because the cluster can insulate itself better than that wooden box. So the bees are like, this is stupid. So they use their cluster and their mantle to stay warm. They don't use the enclosure. In both conditions, so the insulated box, the bees are actually using the enclosure, either on purpose or not on purpose, to stay warm. They're not really clustered. Okay, so they start clustering in my boxes around -16 Celsius. Back to the wooden box, this is the key one, is once brood rearing starts in that box, in that wooden box, okay, heat loss becomes very strong. The relationship gets really strong, more than 0.9. So it says there's a strong connection here. Okay, so it means that, say you get a cold snap and it's -15 outside, that wooden box is losing 30 watts of heat just through the enclosure walls. I'm not even talking top entrance and ventilation, just pure conductive heat loss. Okay, so 30 watts energy-wise is about 3 pounds of honey consumed per week. Okay, so this is why down south, once your bees start brood rearing, especially in the beginning, they're losing because they're maintaining the box temperature now. So this line here becomes the driving force. Oops. When there's no brood, it's irrelevant. The cluster is the driving mechanism. But once brood rearing starts, they're trying to heat the box now. Okay, and that's why they're losing so much heat and the risk of starvation. But in my boxes, or people who use polys or wrap their colonies with minimal or just the perfect amount of ventilation, they don't have to worry about starvation if they properly fed or made sure the bees have enough honey going into fall. Okay, so again, bees are special and I love them, but they cannot defeat the laws of physics. They still have to follow some key principles, okay? So I'm not gonna go through all the detail, but there's three types of heat transfer. There's conductive, so that's through a solid surface, so the hive wall conducts through. Convection is temperature differences in the air inside the colony, the difference between inside and outside air. And radiation is the sun. Or in a cluster, when the cluster's tight and they're closed because it's really cold outside, then the heat loss from that cluster, there's a bit of conductive heat loss, and then there's radiation radiating off that cluster. So if you have no honey around there, most of that heat just gets dissipated and it's lost. But if there's honey around that cluster, the honey will absorb some of that heat. It's like a radiant heater. A key factor for ventilation is this stack effect. So the buoyancy, I'll have a specific slide for that. Okay, so it's like a hot air balloon. Warm air wants to rise, cold air wants to drop. airflow. So windy days. So if you're going to have a top entrance and you live in a windy place, make sure you protect those top entrances from direct wind contact. Okay, because I think it's around 20 kilometers an hour is enough to reverse the direction of flow in that top entrance. Bernoulli effect, it's the top entrance, the size of that is what actually drives how much air flows through that colony. Okay, it's not the bottom entrance. At some point, the bottom entrance limits it, but the limiting factor is the size of that top entrance. So again, natural convection, single entrance versus double entrance, there's some differences. And again, it's driven by the temperature difference. Thermal mass it's like a concrete floor, a passive solar house, those types of things. So in a beehive, it's honey frames. Okay, honey frames is a wonderful heat collector. And I'll show you a couple of examples of what bees can do with it. So I ran some experiments last year. So I think it dropped from -5 to -35 in 5-6 hours. So before the bees were impacted by that cold, it took about 8 hours. Okay, so the bees had 8 hours to adjust. So it was a slow transition. But I had a box with an artificial cluster, heat source, and in a wooden box, and it was less than 1 hour before that box basically dropped in temperature. So the bees would have had very little chance to adjust and they would have been stressed out. So a portion of the bees probably would have died. One big cause of mold and condensation in colonies is thermal bridging. And that's a crown board or an inner cover, those types of things where there's a wooden structure sticking out. Those are it's a thermal bridge it's a heat sink, so it's sucking out heat and bringing in cold, and that's where you get condensation and mold. This chart here I use it quite a bit, and this is I think it was Southwick, Sealy's used it, and it's basically how much energy is the cluster generating versus temperatures. When you're in a non-insulated colony, you're using the ambient temperature because temperature inside is equal to the temperature outside. But when you're in an insulated colony, this relationship no longer valid. So I've been adjusting it with a local temperature. Hence the reason I put sensors below my clusters. So it gives me an idea of what temperature those clusters are exposed to. Just to give you an idea, 10 watts is about a pound of honey per week. Okay, for every pound of honey, there's an excess of about a cup of metabolic water that the bees need to manage. Okay, so this is assuming about 20,000 bees in the cluster. Okay, so that's a lot of water that the bees need to manage. So I use these types of relationships and some of these calculations to help me do what ifs and then learn the different relationships between different variables so I can get an idea of what the impacts are. Okay, so I'll skip over this. So if you're curious, you have access to the presentation there. These are just explanations of what the different types of heat transfers are. So how does insulation work? Basically, heat naturally wants to flow from hot to cold. Okay, so if it's cold outside and it's hot inside, the heat wants to flow out. So it's always trying to head to the lower energy state. Insulation slows this transfer down. Okay, I notice a lot of people use cinder blocks or sometimes have their colonies on cement slabs. I'd say in summer is one thing, but in winter, it's probably not a good thing because a cement slab actually sucks the heat out, and it's a sink. And because it never really warms up in winter, it's not very good for the bees. So I'm going to show you 3 scenarios. Okay, the first one is a typical wood colony. So R1 all the way around. So R value of 1 with a top entrance. And most of the heat off the cluster flows up and is lost through the top cover. Any excesses flows out through the top entrance. Most of the condensation happens fairly high up in that colony. The sidewall heat loss is actually quite low because it's the cluster protecting itself. The cluster is keeping the heat inside and not really releasing much heat. Hence the reason there's very little relationship between the heat loss in the walls and structure and the temperature outside. Okay, so in an insulated colony with the top entrance and a lower entrance with a solid bottom board, again, the halo, the heat halo will be lower, so it'll be warmer lower. The heat, sometimes the heat has the cold air coming in has to flow around the cluster because the cluster might be blocking off the airway with their bodies. So the air will flow and then the hot air goes out and it creates a siphon. So it's part of that stack effect, the buoyancy effect. So hot air goes up, it wants to leave. So hence the reason why a lot of the moisture flows out of the colony. And on the backside, a lot of the condensation happens mid-wall to lower wall. And you might get some mold on the backside of your bottom board here. Okay, this next one here is my setup. So I don't use a top entrance and my top is at least 30 R. So it's very well insulated. Okay, I do have screen bottom boards, but they're protected. And remember, we got quite a bit of snow the last few years. So basically there's snow on both sides here. So there's no airflow going through this gap here. So it's just a crawl space. Okay. The reason I like my screen bottom board open is it's backup air if I need it. And it's also cooling air in case it warms up outside. It'll help regulate the temperature so that the bees don't overheat, because it's usually, I'd say, close to 0 to -10 down here. So it helps regulate the temperature of the bees. Because there's no top entrance, the only airflow is through natural convection. So natural convection is where the warm air on top cools down. And I'll show you a profile picture, and there's usually like a cool channel in my colonies. Okay, so the cool channel is where the air can cool down, it'll drop, and then basically flows out. As it flows out, it comes in contact with the cold air coming in, and there's actually a heat exchange here. Okay, and I do get condensation at the entrance, but usually it flows out and there's enough heat coming out to help keep it from freezing. And any excess moisture off the walls here, they just leak down through the screen bottom board, and I don't get the ice buildup here anymore. Okay, and for example, 2 days ago, or was it yesterday, I took some IR, I put an IR camera underneath the cluster and I'm taking a picture upwards, and the bees basically, it was -10, -8, and the bees they're filling the whole box. They're lightly clustered, but it's almost box side to side bees, and the bees aren't agitated, they're just there. So just to show you how my monitoring is set up, so I usually have 9 sensors on the top of the box. On each level, I'll have 2 to 3 sensors below the cluster, and that's the setup. Okay, and for those who are engineering and like calculating things, I put 2 calculations here. One is to calculate the dew point, okay, because you'll probably have a temperature and an RH value, so you can actually calculate the dew point of that air to see where condensation would happen. And then the other one is absolute humidity, so grams per cubic meter, and that there is actually a very important measure because it tells you how much moisture is actually carried in the air. So for example, I've got 9 red temperatures in this diagram. And what I've done is I've modeled the distribution of temperatures just using a couple of formulas and a couple of assumptions. For example, the sensor in the middle here, it's almost 20 degrees Celsius. It had a humidity, relative humidity of 68, which makes the dew point around 13.6. So this 13.6 is actually pretty much the temperature on the outside of the cluster. So when I do my IR and I look at the temperatures on those outside bees, it's anywhere from 12 to 14 degrees. So which pretty much coincides with where the dew point would be, okay? And then this is an example of it has a slatted rack, it doesn't have a slatted rack, and you'll notice that the slatted rack is warmer and the cluster seems looser. And on this side here, it's much tighter. And you can see how the sensor here, and that's the thing with monitoring with only one sensor, is you don't know where the cluster is. Okay, by my 9 sensors, I have a pretty damn good idea of where the cluster is, and I can pinpoint it. So for example, the dew point of the air at this point is actually on the outside wall. Okay, because the gray here and the inside yellow is probably the outside section of the bees. Okay, so the moisture in here, which is very similar, would actually condense here, and the air here gets saturated out here. And this is my control hive, and it just shows at minus 22 outside, the inside temperature is around 19. But what this does is this control hive is insulated, and it has about 60 pounds of honey. So it helps me understand the thermal lag and the impact and how slowly stuff goes. And yeah, I can't really read the chat there. Okay, so I'll get to the slatted rack in a minute there, so it should be good. So not everybody's an engineer or has statistical stuff, but the challenge with taking a lot of data is you get a lot of data points. So I just got myself some statistical software, and it just makes it easier to chart things. So this chart up here, plus another, how many sensors? Another 6, 7 sensors is represented with these box charts. So a box chart is basically a way of representing the distribution. Okay, so for example, if we looked at the first one, the ambient temperature, from all the green, the size of the green here means that 50% of the data is held within this box. So between -5 and close to -20. So that's pretty much 50% of the weather that we had in my data. That little line in the middle here, that's the mean or the median. Okay, so that's basically the average temperature was about -12. From this leg to the top of the box here, that's another 25%. And another 25%. So basically, once you get used to these charts, it helps you visualize data much easier, and it's easier to compare 2 data sets with each other. These dots, those are outliers, okay? 1 or 2 values that were way out there, outside that normal distribution, or that distribution, I should say. So I'm not going to go through this much. But just so that when you have a lot of insulation on top, the cluster looks more, and especially if your sidewalls are insulated, the cluster has more of a hemisphere shape than the typical quoted spherical shape. Why? Because the surface here is a better insulator than what the mantle can do. So the bees will tend to do this. So it's probably more of an elongated sphere. Or hemisphere. So, but what I've done is I've modeled my data using hemisphere as my geometry. And it works really well with a slatted rack, but a non-slatted rack, it's like a hybrid between these two, so it's harder to model. And because the top surface here is really well insulated, it means that the exposed surface area of that cluster is actually less than a sphere. So it's actually more beneficial for the bees. Okay, so LE is low exposure because it's actually against this side, this top wall here. And HE is high exposure, and that's the one exposed to the temperature. So what I do is, because I've got 4,000 points, data points, so temperature points, times 30 some sensors. So what I do is I calculate heat loss and all these different values, honey equivalent and water generated and all that. And what I do is I calculate this every hour, and then it gives me charts and things that I can use to visualize different relationships. This is complicated stuff, but basically it helps me understand the volume of the cluster versus outside temperatures, how much heat loss versus outside temperatures, probable metabolic rate versus outside temperatures. Using different profiles, I can calculate heat loss and airflow and all that type of stuff. So, and the numbers are pretty damn close. So for example, here it's around 5 watts at minus 40. So at the coldest here, it's about 7. So the numbers actually add up pretty good with heat loss through the bottom entrance versus heat loss through the enclosure. If you add both of those up, it actually adds up pretty damn close to the my calculated average metabolic rate that the bees would generate. Up here, all these colors are just the different gradients of that cluster, and I'm using a hemisphere shaped versus the outside temperature, and it gives me an idea of what the cluster is doing over time based on outside temperature. Okay, and you can see that in March here it starts warming up. I put my pollen patty over here, and you can see that the temperature zone of V30 is just the volume at 30 degrees Celsius. You see the portion of the volume at 30 C is growing, and so that tells me that it's starting to brood up. And then the outside temperature range is 24, so pretty much the whole box is at 24 degrees, with the inside core, most of it's at 30. So that was the most complicated slide. I apologize. So we'll move on, because there might be some techies here and people interested in this stuff. So I just wanted to show what you can do with data. So when spring brood rearing starts. Okay, so this is, let's see, this colony here is that wooden colony from Virginia. Okay, so this first chart here is when there's no brood in the box. And the reason I know there's brood is the temperature is not 95F or 35C, but once I see the temperature hit 30, I know there's brood in there, and then the data would be categorized here. Okay, so you can see that the outside temperature and the controls are pretty the same, so that's the same relationship. And then the average temperature of the box is actually pretty close to ambient. Okay, there's a little shift here, and that's just because there's a cluster of bees there generating some heat. And that's that 0.9 correlation relationship, R squared. Okay, and then over here, once brood starts, you can see the ambient temperature. And then the average temperature actually is close to 30 C. So now the temperature difference, so this is why this is correlated 0.9, it's actually close to 100%, but here the correlation dropped to 0.2. Okay, and then the correlation was actually more from the heat loss correlation. So this red line here is equivalent to how much energy, because that's the temperature they need. So from the bottom here to here that's how much heat they need to produce to maintain these brood nest temperatures. Just so you know, heat loss again is surface area times temperature difference divided by R value. Okay, the metric calculation is slightly different, but that's in general. So the thing with a double box, there's more surface area. Okay, so there's higher heat loss. So that's why even if you're in a wooden box, it's important that you manage volume, because the wooden box in a double will have quite a bit of heat loss. This is again just a visual. I can calculate the heat loss in these walls, and this was early brood rearing in this Virginia colony. It tried 3 times to bring the temperature up to 30, 35 C, but every night the temperature would drop. Okay, so what happens there is the bees aren't able to maintain the temperature, so then they quit. So then they just dropped it back down to 20 degrees, typical cluster temperature with no brood, because they can't, it's too much energy. They couldn't bring up the box to right temperature. Okay, so you can see that's where the heat generation, so 4 pounds a week equivalent of heat loss. In my poly colonies, if I do the same calculation, you can see that it's like 2-3 watts, 1 watt of heat loss. So it's less than a pound, less than a 0.09 pounds per week equivalent. So really there's no heat loss. So the bees are easily able to maintain that temperature with low consumption. I'm going to skip that one, and I'm going to skip this one. But it's just, again, to show that, so again, these are week numbers. It's consuming about a pound, it's losing about a pound per week of honey via heat loss. But once the cluster starts generating enough heat to start producing brood in March, this is where the main driver becomes the enclosure. Okay, so that's one that I'm going to drop. This is just comparing different volumes. Okay, so you got your doubles, you've got your singles, and then you've got a double wooden colony. So this first chart here is the outside temperature. And these 3 colonies were all in the same location, hence the same temperature. And over here, so the average temperature, you can see the wider this is, the more variability you had. Okay, so you can see it's much warmer, but the variability is really, really high. The low temperature on the average is around 15 C, and up here it's all over the place. So when I do my time lapse of the cluster, here it disappears because it gets so tight that it doesn't release any heat, so the sensors actually can't see it. Over here, the max temperatures. So you can see that there's always, it's a very tight. So this cluster here was actually running quite hot, but you can see how it's very low variability. The floor is at 18 C, which is right. That's the floor. But the wooden colony, again, there's no distinct max temperature because it's all over the place. Because it's cluster driven versus enclosure driven. And then the minimum temperature, again, it's all over the place just because. So in English, so clustering facts is clusters start happening at 14 C. They're the tightest at minus 10 C. Okay, so in my case, at minus 40, 35 to 40, it's the only time my cluster is fairly tight because it's cold. But in a wooden colony at minus 40, it wouldn't last very long because it's so damn cold, and the cluster would just run out. Hence the reason we have to insulate in most places in Canada. Let's see, average, I'll just skip over that. Slatted rack, just to answer your question. For singles, it works great. For an insulated single, I'd say that's my standard now. It reduces heat loss below the cluster. It reduces the airflow. It gives a really nice place for dead bees to collect, so it doesn't clog up the lower entrance. I do remove it in early spring and clean it out because it does create a cold gap down there. Because it's in spring, that cluster or those bees are at their weakest because it's a bunch of old winter bees that get easily stressed out. So I remove it and tighten it up. I insert my insert in my screen bottom board, so that way the bees can create a really nice nest. I'll let them run for 1 or 2 cycles, and then I'll put the slatted rack back on. In summer, it helps with reducing bearding. It actually helps me with my swarming because I don't really get swarm cells in the bottom box anymore since I started using slatted racks, and most of my swarm cells are in the top box, so it's a lot easier to find. I don't need to do full inspections. And again, it helps protect the bottom section of the lower brood box because we do get cold evenings here. And this is that picture I took from yesterday. So this is the bottom edge of the lower frame. So it's just on top of this here. And this is the temperature above here. So you can see 13 degrees pretty much at this surface, and it's 22 right now on top of that. So, and it's pretty much side to side. This blue area here, this is that ventilation channel, okay? Because it's cooler. They're actually they're blocking this off so they can release warm, moist air into this cool channel, and then it'll drop and then condense out or just go out the front entrance. And again, slatted rack, because right now I've got a single with and a single without a slatted rack, and I can see the difference from basically how much heat. The non-slatted rack is more clustered, and there's a bit more variability than the slatted rack one. So it just tells me that metabolically, it's more efficient than the non-slatted rack. Okay, so heat loss is a bit higher for the slatted rack colony than the non-slatted rack colony. So it's about 1.5 pounds more as of the end of January. But the estimated metabolic rate is much higher in the non-slatted rack because the cluster is exposed to colder temperatures. So you can see that even though it's running a bit hotter, losing a bit of heat to the wall more than the other one, it's way better than the cluster having to generate more heat. For a double in the winter, there's less impact because there's so much volume below the cluster anyways. So I'd say in the winter, the impact is minimal versus a single. So these are the temperatures above the slatted rack for the different months. So November, December, January, February, March, and April. And these are the temperatures below the slatted rack. So there are some differences, but not significant. So, but for a single, it's great. So for a single, there's about a 8 to 12 degree difference, or about 8 to 12 degrees difference. So because I've had both, so this difference here is this is a colony without, so you can see it's exposed to colder temperatures than one with. So this is the cluster temperature that it's exposed to, and over here you can see it's much colder. So -20 versus, let's see, -7. Managing moisture, regardless of what you do, you will get moisture. And over here, again, it just shows I had sensors, humidity sensors with in all my 4 corners of the colony last year. So this was humidity sensor temperature in the middle of the colony. This is the dew point. So you can see that the corner temperatures and the sidewall temperatures are colder than this dew point. So it means there will be some condensation. But if you look at the temperature, it's actually fairly warm. So it's actually warm water. So the bees can just consume it, or it's not chilling, cooling water. And that's the danger with colonies with bare bones. I recommend people use insulation in their top covers because it helps in summer and it helps in winter with that condensation falling on top of the bees. And in the summer, it actually helps reduce the heat stress that the bees would get because of the warm sun. And the bees are more able to stay cool. Over here, these are just the relative humidity plots. And again, usually between 60, this is actually ambient. And so the colony last year was a bit humid, but anywhere from 85 to high 70s, mid 70s was normal, but they did well anyways. So bees increase the temperature to increase metabolic water. So if it's too dry, they'll actually generate heat to produce more moisture in the air. If they want to increase the RH to near saturation point, they'll actually lower the temperature. So they'll lower temperatures in probably a location in the colony, so the sides, or I'll show you an example of how the bees can actually heat the inside of the colony to generate condensation and probably get rid of some CO2 or something like that. So the other thing is they actually use winter brood rearing to manage excess water. Okay, so it's actually a good thing in the right context. So if you've got too much water and they can't cleanse, they'll actually, a lot of times, hence the reason that usually after solstice, mid-December, early January, most colonies will start brood rearing and they'll have a small brood nest in there. It's to help manage water. Again, by maintaining higher levels of CO2, it actually calms the bees down. It puts them in a torpor, and then they're able to lower their metabolic rate. So by lowering their metabolic rate, they're generating less moisture. And you'll notice that there's a vicious cycle here. So the more heat loss, the more the bees need to generate heat to stay warm, the more moisture they generate, the more honey they consume. And it's that cycle. Okay, so for example, in 210 days, my bees need to manage 25 cups of water versus the colony in Fredericton in Maryland, in 90 days, they have to manage the same 25 cups of water in a much shorter time frame. Hence the reason why it's riskier. Bees hold water in their bodies. And like I said before, the DP, so the dew point, seems to coincide with the outer edge or inner edge of the mantle. And here my guess is it so the bees can reabsorb the water, condense it closer to them. I'm not sure how they do it, but it just seems to coincide. And for those in northern climates, our bees tend to not get many cleansing flights. So managing water is critical. So too much heat loss means chances are they're generating too much moisture, and chances are we might get into dysentery. Thermal bridge is these bright spots. This is just an IR picture. So when you do IR pictures, anytime you see bright spots, it's heat loss. And this is where condensation happens. Okay, so it means it's losing heat. These little tabs here, I'll show you in the next picture. So you can see the mold over here. So now my sensors, you've noticed I've chopped these plastic things off. So now it's just the sensor part. And I've taken these things out, so there's no cold air coming in. And the other thing I do now is I tape all my seams so that no cold air comes in. When you put two colonies together, the cold spots is on the opposite backside, if whichever side has the lowest insulation factor. For example, what I do is my sides and my back have more insulation than the front, because I want my front to be where the condensation happens. And the bees tend to escape towards the back during really, really cold nights. This is again to show the difference. So I think if you watch YouTube there, this is Jim Vino. He gave me some data to look at for his ultra insulated colonies. These are different. He's got different genetics in the different boxes, but no top entrance, very well insulated. And you can see they're much tighter. They're fairly consistent temperature wise, RH wise. They tend to manage well. He does have a few with smaller clusters, and it's probably more variability here. So this is absolute moisture. So you can see there's a bit less control here, but fairly tight versus the ambient. And then over here it was a Kentucky colony. Somebody sent me some data with no brood. And again, you can just see that they're able to manage RH, but the challenge with RH is it's temperature driven. So it's relating to temperature. So it's not a good indicator. So the best indicator for control over humidity in the colony is actually absolute humidity, and it's all over the place. And over here you can see it's the ones with close to zero might be faulty sensors, but they're able to maintain a floor versus this one here has a wider range. I'll skip that. So this one here, we're almost getting there, is an example of the bees heating up the box with no disturbances. Okay, it was this year I've had quite a few. This was last year. It was -40 out. You can see the cluster here. These are Celsius, so the bees are cozy. The outside temperature here on the outer edge, inner edge is 3 Celsius, 2.7. Outside is -40. So the bees are fine. They're comfy. And then 6 hours later, it's still -35 out, and the bees are starting to heat the box. Okay, so they've increased the temperature by about 4 degrees to 25, and they're heating the inside of the box. 6 hours later after that, still fairly cold, but now the whole friggin' box is warm. Okay, and then by midnight, they're starting to cool things back down. Okay, so this here is me looking at this in a chart form. And the green line here is the surface area of the cluster, so the size of the cluster versus different temperatures. And the thing with dew points and temperatures is every time you see a crossover point, it's an indication that condensation or some type of moisture happened. So as the bees cool this air down, we're going to get condensation on the sidewalls here. Okay, so it's clear. So it's actually, again, it's fairly warm, so it's actually warm drinking water. So the bees can access that water without being too much in danger of getting chilled, because it's actually warm. And you can see how they ramp the temperature down. The size of the cluster went back to the cold level, and it took about 5 days before it going back to that floor again. And then there's another heating event here where it's more of a atmospheric, so the outside temperature started warming up, and then the cluster basically opened up again. So bees do heat the inside of the colony. Why, I'm not sure 100%, but they do it quite often. Here you can see a couple cycles of heating, and then taking a few days, three days to cool back down. So while they do this, they're actually heating up the frames at the same time. It's a byproduct of that. So chances are they heating up the frames, creating condensation, pushing out CO2. But by doing that, this is the lag. This is them pushing a bunch of heat, because the heat is not lost to the environment because there's no top entrance. It's stuck in the box. So it's actually being stored in the honey frames, and then it's slowly being released. And that's what this is. Okay, and for example, if you tap your colony or if you disturb your colony, it's actually, this is an example of me disturbing my colony and then measuring how much heat is actually generated in that box. And so it's quite a bit. So practical applications is if you've got, I've always got colonies with undrawn frames and I pull them out. So I won't overwinter a colony with undrawn frames or partially drawn frames with not much honey because it's pointless. So I will fill this gap with fillers. Okay, so I'll put fillers in there. These are insulated fillers. So inside this box here, there's a bunch of styrofoam, and it's just to shrink the size of the colony. So this is one way I control the volume, is I put follow boards or fillers to basically squeeze that colony together. The other thing you'll notice is honey frames around the brood. You rarely see, or you never see, honey below the brood, unless it's a bottom box, but typically there's no honey below the brood. It's always above or on the sides. Remember, they want to keep this inside here, the brood area, at 35°C. So any heater bees that generate here, the heat wants to rise, it'll get collected in this honey. The other thing with this honey is it usually pinches out. Okay, so now, and there's typically maybe a bit more than a bee space here, but all it takes is a couple of bees to fill this gap. And now basically they've just created a block. So any heat that's generated out here gets pushed up, it's slowed down and gets collected in this honey. Hence the reason it's really important for you to have a lot of honey frames in there. We tend to put candy boards up here because we took too much honey. Candy boards don't hold heat. Honey does. Okay? And this is, if it's in a honey frame or a nice brood frame with honey around it, it means the bees can manage the heat and hold it in here, even if your box is not insulated. Okay? Because that honey does have decent insulative properties. And then they release the warm air on top. It'll cool, because if the cluster's over here, it's hotter here, so the air will tend to flow out along the sidewall. It cools, condensation happens, and then it flows out. So one piece of advice is take out those empty frames and backfill. People have a misconception that bees won't overwinter. If you manage heat loss, they'll do fine. Especially if you've got, say, 30, 40, 50 pounds, whatever amount of honey you need to overwinter in your area. This is just proof that, again, there's airflow out. This is hoarfrost at my front entrance, and it tells me that moist air is coming out on a really cold day. In the summer, I still don't use top entrances. My landing boards are soaking wet during nectar flows. It just tells me the warm air is coming out. Our mornings are pretty cold, so it just condenses out. So it's telling me that that's how they dry their honey in the summer. Let's see, this one here is just to show 3 relationships. Okay, so we've got airflow in no insulation. So if you remember convection currents, stack buoyancy effect, and all that type of stuff, it's driven by temperature differences. If you have no temperature differences, you have very little air movement. Okay, so when you don't have insulation, you have very little natural air movement, hence the reason why you need a lot of top ventilation to get rid of any of that excess moisture, or else you'll risk having some condensation. So there's a balance you need to find there. Okay, so if you insulate, you start getting fairly big differences, especially in really cold days, between inside and outside temperature. So now the size of the top entrance becomes really critical, because if it's too big, you're going to lose a lot of heat out of that top entrance. Because I've tested top entrances out, you put your hand on it and it's actually extremely hot air coming out. Okay, so these are just showing the difference between a 3/4 inch hole versus a 1 inch hole for singles and doubles. And this is the size of the lower entrance. So you can see that at about a 2 inch square inch bottom entrance, it pretty much flattens out, and that's that throttling effect of the top entrance. And you can see that just that 1/2 inch diameter difference doubles the airflow almost. Okay, and then the last one with no top entrance is it's purely convective, natural convection. Okay, so the bees might fan a little bit, but I've never seen it. And it's natural because it's warm in the colony, especially on top. The air cools and the air naturally flows out. And usually I'd say my estimate is about 0.5 to 1 liter per minute of airflow out of that enclosure. So again, with top entrances, you need to manage the size of that top entrance. And this is where I typically recommend no more than 3/4 inch diameter hole if you're going to insulate. And then I recommend don't use an open screen bottom board, because then you'll get too much flow through. So, and this just goes and shows the magnitude difference. Here are the volumes of the different sizes. So what you do is you take this flow rate, divide this by that, and it gives you an idea of how many minutes it takes to change all the air inside that box. Okay, so this one here, very big difference between inside and outside. And you can see that the difference between a double, so 1 inch hole versus a single 1 inch hole, is 60%, more than that, yeah. So it's 10 versus 16. And double to double, it's almost half. So it's just over 8 liters versus 16 liters. So that's the difference. So the more experience you get, the more you test things out, the more you'll be able to see these differences. So again, in non-insulated colonies where T in is pretty much T out, you can see that the airflow is not very high. But what happens is once brood rearing starts, the temperature inside and outside increases. Okay, so what that does is actually increases the airflow and pushes out more heat, and you'll start losing more heat as the temperature difference grows. Okay, so I'll repeat that. So because they're trying to maintain the whole box or a big portion of the box at brood nest temperature versus the outside temperature, what that does is it actually increases the airflow now. So increasing the airflow actually increases the heat loss, which increases the bees wanting to generate more heat to keep the brood nest warm. And you can see how at that point it becomes a vicious cycle. So when I use the top entrance in my insulated colonies, I should have used the plug during really cold temperatures or a reducer to reduce the amount of airflow. Okay, so this is the risk of non-insulating. If it gets cold outside and they're trying to brood rear, is the heat loss just goes exponential, and that's the risk that they have. 3 more slides. This one here, again, it was just to show, I found a model showing how at different wind speeds, hitting a top vent versus a bottom vent. This is actually a building with 2 windows. Just so you know, when we build the plane, we design a plane, we'll design it, we'll design a 6-inch model or a 12-inch model, and we'll put it through wind tunnels and stuff like that. We'll test it out, test all the dynamics, and then we'll actually build a real model, scale model later. So the relationships hold. So it just shows that protect that entrance. So this is in Saskatchewan, the Pedersen apiaries, they actually staple these cardboard protectors on their top entrances because they have lots of wind. Most of my bee yards have pallet fences like that, so it creates wind block, so it helps reduce any direct wind hitting those entrances. So my winter setup. Okay, so I overwinter my nooks hugged in the middle of singles or doubles. You can notice the vapor barrier tape. I block all the seams off because I don't want any heat loss. What this does, it helps create an air bubble. So all these colonies now are sharing heat. One thing I will do in the future is I'll put styrofoam below my nooks because I need to protect the nooks because they're more sensitive to fluctuations because the cluster is much smaller. So I'm going to start putting insulation below my nooks. Still leave the vents open, but I want to insulate below it to protect it. These are my stands. So I built a deck. I had some 2x8s, and basically this is an open space right below my screen bottom boards. So any moisture flows down here, and this I think is October. Doesn't take long for us to get some snow, so I can put snow around it to prevent any airflow from going underneath here. Okay, so these boxes, this is actually a double with a medium box on top. This is a single with a deep box on top, a single with a deep box, a double with a medium, and the medium and the deep box is on top. What I do is I cut out this styrofoam. This is 2-inch. I have my feeding insert in here. So I've put styrofoam in here now, and I just leave the slot open, and I put in the meantime, I just put sugar, dried sugar in there, and I sprayed with water, or I put some fondant, and then styrofoam on top. And I actually have a little piece of plywood, put that. So what it does, this is how I get that R20 or R30-40 on top of my colonies, is that's how I do it. Eventually I put a bubble foil wrap around all this to create a wind barrier that protected against the wind and create an air bubble. And you can see how I've taped the seams here. And then to protect because we get quite a cold north wind here, so I protect the north side with some plywood just to enclose it. The challenge with polys is you do get condensation along the side walls. So a lot of my boxes, I use 9 frames, and then I put these, this is pine board, so 1x10 pine board, and I just notched out some little notches here so that it fits in like a frame. Okay, so it helps with, it allows excess moisture to be absorbed by the wood. You can scratch it up to try to get the bees to propolize it during the season. And the other one is it prevents flowing water, like again, along the side walls, which the bees tend to drown in if there's too much. So again, my decision point is early to mid-August, and this only works for insulated colonies, okay? Because the challenge is the volume per bee. It's still very important for non-insulated, but because I know what the heat loss is, I know that for example, a nook needs 20 pounds to survive from October to May. Okay, so if my nook has 20 pounds of honey, they're fine. If they didn't have insulation, then they probably couldn't go that long because they'd run out of honey and they'd starve. Okay, so same with my singles. A single needs about 30 pounds, 35 pounds. So I overwinter with probably 60 pounds. My nook, I need 20 or 15 to 20. So I overwinter with 3 to 4 good honey frames. And then basically the old brood nest in the middle. And then my doubles, I try to go over 100, so 60 per box. And this is just another example. This was mid-August, so it was decision time. It was a really weak cluster because it was a late split. I had issues with the queen, so it took forever to get covered. So back in August 15th, I put these filler boards. This is styrofoam, so the bees don't chew it. I just taped it. Now this is a 2-inch version. This is a 1-inch version, and then I've got these 1x10 inserts. Put my pollen patty. Luckily, the colony that was just next to it had plenty of brood frames. So I took one big one, shook the bees off, and stuck it in here. And then lo and behold, a month later, it had plenty of bees. The queen was going crazy. So I expanded it a bit. So you can see how I just left one follow board with 2 wooden inserts and then one follow board. So this is plenty of bees to overwinter here, and it had plenty of honey, so it should do fine. So that's how I manage my volume. And then the next one would be to put it in a 5-frame nook if I wanted to. So I know it was a lot of info, and I know already which slides I need to cut out for the main presentation that I'll be doing, but any feedback will be good. You can send me an email. If you've got a question now, you can unmute yourself. It's a lot of info, I know, but I guess it's 5 years of me trying to figure things out.